When we think of scientific theories that completely change the way we think of reality, a small handful of names pop to mind. Copernicus, Darwin, Freud, Crick and Watson, but foremost is the name Albert Einstein. Einstein radically changed the way we think of space, time, mass, and energy, the fabric of the universe itself, and everything in it. Einstein forced us to re-envision the very nature of reality, challenging both common sense and the heavyweight champ of the history of physics, Isaac Newton, whose theory of motion and gravitation reigned supreme for 300 years. Now, the name Einstein is synonymous with genius, but it took a while for the world of physics to appreciate what Einstein had done in 1905 with his special theory of relativity. In fact, it took Einstein himself a couple of years and help from one of his old college professors to fully grasp it. We refer to 1905 as the miracle year, a term historians of science originally applied to 1666, when Newton developed his theory of space-time and motion. The miracle year now refers to the time when an unknown patent clerk in Switzerland published 5 papers that changed the way we see everything. Einstein was in the patent office because he couldn't get work as a scientist, despite having graduated with good grades from a good university. In college, he thought he knew better than his professors, refusing to do the experiments they assigned, refusing to study the classical theories they presented, refusing to speak to them in the expected, respectful manner. He was arrogant, impudent, and had a penchant for skipping classes, preferring to discuss the latest theories with his friends at a local coffee house. So, after graduation, when he applied to literally every physicist in Europe for a job as an assistant, all of them turned him down. He had no jobs and no prospects. But he did have a friend whose father had connections, so he got a good government job. Life for Einstein in 1905 is not what one would think is fertile ground for an intellectual revolution. Einstein had a dysfunctional marriage, a newborn child, and a full-time job. Yet, he published 5 papers that year that changed the course of history. The first was his doctoral dissertation, developing a mathematical model that's still used in the mixing of cement, the packaging of ice cream, and the development of air fresheners. The second used this mathematical machinery to show, beyond any reasonable doubt, that atoms exist. The third, for which he won his Nobel Prize, changed forever the way we understand light. The whole picture of light waves had to be altered, so at least some of the time we had to think of light as being made up of particles. Now, these alone would be a lifetime's work for a history-making scientist, but they were just March, April, and May of 1905 for Einstein. June and September brought the 2 papers that introduced the theory of relativity, the theory that would make Einstein famous, launch the nuclear age, change how we understand the foundation of reality itself. To see how revolutionary the theory of relativity is, we need to think about the view it replaced. The picture of space-time and motion we get from Isaac Newton makes so much sense to us that Immanuel Kant argued that the human mind can't even contemplate it being false. For Newton, space and time are absolute and independent entities. Space, Newton thought, is fixed and immovable. It's a giant piece of 3-dimensional graph paper nailed down underneath reality. If you had a God's eye perspective on the universe, you could give every point and object a unique address, locating it in this absolute space. Space is where things are, and all things are located at a specific spot at every instant in time. Time, too, is absolute. It flows constantly and regularly. It's as if God had a perfect Rolex that never needs winding and never needs resetting. Time ticks off moment after moment, regular as it goes, and we can talk about what's happening at every point in space at any one moment. What's happening at those points is governed by the 4 basic laws we discussed in the second lecture, the 3 laws of motion and the law of universal gravitation. Now remember, the first law deals with objects that have no external force applied to them. If something's not being pushed, then it will continue to move in a straight line at a constant speed. Picture again someone on ice skates. The person is still, he remains still. If he's moving, then unless something changes his motion, he'll continue at the same speed in the same direction. The second law applies to objects with a force applied to them. Push something in the direction it's already moving, it speeds up. Push in the opposite direction, it slows down. Push it to the side, it changes direction. The heavier the thing, the less the change. The bigger the push, the more the change. The third law tells us what happens to the thing that does the pushing. This is the action-reaction law. There will be a force felt by the pusher, which is of the same amount as felt by the thing pushed, but in the opposite direction. These laws allow us to explain everything we see on a billiard table, and when we add the law of universal gravitation, according to which all objects attract each other with a force proportional to the product of their masses and inversely proportional to the square of the distance between them, we can now account for the tides, the movement of the planets, even predict the coming of comets. What's interesting is that these rules give us the same results for all observers moving relative to each other in a straight line at a constant speed. Now, suppose I'm at the airport, standing on the right-hand side of a people mover going 2 miles an hour, while someone with a connecting flight in a roller bag passes me on the left walking at 5 miles an hour. Someone sitting at Starbucks would see me moving past at 2 miles an hour and the other person moving at 7 miles an hour. I would see the coffee drinker moving backwards at 2 miles an hour and see the through traveler going past me at 5. If the coffee drinker dropped her phone, all of us could use Newton's laws and calculate exactly the same effect for the collision of the cell phone and the airport floor. This makes sense to us, but it leads to a problem for Newton. If the laws hold for all people moving at a constant speed in a straight line relative to each other, then the laws wouldn't allow you to find out which person is really at rest. We could never find out whose space is absolute space. If absolute space is real, then our science should be able to determine its properties. But Newton's theory, because it holds equally well for everyone not speeding up, slowing down, or turning, cannot do this. Scientists thought that the workings of the physical world could be explained by two categories of forces. Motion and gravitation were covered by Newton's theory. Electricity, magnetism, and light were explained by Maxwell's equations, 4 laws named for the Scottish physicist James Clerk Maxwell. They set out the relations between changing and unchanging electrical and magnetic charges. When the amount of electricity changes, it results in a magnetic field. When the amount of magnetism changes, it results in an electrical field. Combine these equations, and interestingly, you get the equation that governs the behavior of light. It has the form of a wave equation, thus light was thought to be an electromagnetic wave. Add to this various ways that light from different sources add, subtract, and interfere with each other, and physicists were sure that light was a wave of electromagnetic energy. But waves need something to do the waving. Sound, for example, is the result of waves in air. No air, no sound. But we get light from stars across vast regions of empty space. This must mean that space isn't actually empty, but filled with something that can carry the electromagnetic waves. We called this the light-bearing or luminiferous ether. Finding evidence of it became a major task for physicists of the 19th century. It had to exist, not only because waves need a medium, but because of a strange quirk in Maxwell's laws. The laws include 2 constants, epsilon naught, a number that appears in the electrical laws, and mu naught, one that appears in the magnetic laws. If you multiply them together, a constant times a constant, you get a constant. That is another fixed number. If you take the square root of it, you get another constant. If you take its inverse, 1 divided by the number, you get another constant. It turns out that this constant is the speed of light. That means that the speed of light is a constant. That can't be right. No velocity can be a constant. Go back to the airport and stand on the people mover, right? Your state of motion will cause velocities to increase or decrease relative to other observers who are walking past you or sitting in Starbucks. So, if the speed of light is a constant, then it must be a constant with respect to something. And physicists figured that something would be the luminiferous ether. This was a happy thought because the luminiferous ether had to fill all of space, making it an aspect of Newton's absolute space. By detecting it, we would thus have experimental confirmation for Newton's state of absolute rest. Finding the ether solves both Maxwell's and Newton's problems. Physics at that point would be pretty much done. Of course, life is never that simple. The American physicists A.A. Michelson and Edward Morley created an experiment to detect the Earth's movement through the ether using light and mirrors to make an incredibly delicate measurement. They built the setup, took the data, and what it showed was nothing. They couldn't find the ether. Without the ether, we still had no reason to believe that space exists as a real thing as Newton demanded. The underpinning of our entire view of the universe remained unsupported. It's not that we didn't believe it. We just needed to justify what we thought was true. This was the state of physics that Einstein inherited. He was fascinated with the work of the Dutch physicist H.A. Lorentz, who was in turn fascinated with the lack of a result from the Michelson-Morley experiment. Lorentz couldn't understand what was happening, but realized that you could at least account for things mathematically if you treated lengths as if they contract in the direction of motion. I mean, of course, things don't squish as they move. That's bizarre. But if we treat things as if they do, then the equations work out so that you have a theory of motion that isn't Newton's, but works with Maxwell's theory, constant speed of light, and the result of Michelson-Morley. But what does it mean? This was the question that Einstein was thinking about with a friend one Saturday in 1905. After a day of kicking around ideas, he caught the train home and, walking away from the station, glanced back at the clock tower to see the time. Suddenly it hit him. He wasn't seeing what time it is, but what time it was. Looking at a clock requires light to bounce off the clock face and travel to you. As such, you see what time it was when the light left the clock. Now, if you're walking away from the clock, the light not only has to get to you, but also has to catch up to you. This would mean that the clock would run slower according to observers moving away and faster for observers moving towards it. It was a revelation. Maybe it isn't just lengths that change, but durations also. If time depends on your state of motion, that changes everything. Einstein rejected the idea of a luminiferous ether, preferring a very different, simpler picture of reality. Consider a magnet and a coil of wire that's connected to a circuit. If you hold the coil of wire still and move the magnet back and forth inside, you create a current in the circuit. If you hold the magnet still, but move the coil around the magnet at the same rate, you get the same current. It doesn't matter which one's moving, just that they move relative to each other. But Maxwell's equations give different explanations for the different cases. Different explanations if we assume there is an ether. If, as Einstein does, we reject the ether, then all that matters is the relative state of motion. The different explanations of the current are not really different, just different ways of describing the same thing from different perspectives. To figure out what that view entailed, he sets out two postulates, assumptions that he lays down as the heart of his theory. First is the constancy of the speed of light. That is, whether you're walking towards, away from, or are at rest with respect to a light source, you always measure the same speed for the emitted light. Second is what he followed the French mathematician, physicist, and philosopher Henri Poincaré in calling the principle of relativity. It says that the laws of physics will be the same for all observers who are not accelerating relative to each other. When you're driving, if you slam on the brakes, mash the accelerator pedal, or jerk the steering wheel, you will feel a force pull on you. But someone watching from the side of the road wouldn't see it as a force acting on you, but the result of your acceleration. There's a difference between your perspectives about what forces exist. But if you're moving at a constant speed in a straight line, there is no difference in the forces you two would posit. That means you would use the same laws. From these two principles, Einstein figures out the equations that allow you to translate between physical descriptions that would be offered by different observers. As Lorentz points out, it would mean that when you're moving, lengths you measure will be squished in the direction of motion. If you're walking with a pen sticking out straight in front of you, the pen would get shorter, but not thinner. The closer you go to the speed of light, the smaller the pen gets. For Einstein, it's not, as Lorentz claims, as if the pen shrinks in the direction of motion. It does. Lengths move from a real property of the world itself to a property of perspective. If I ask you if this pen is to the left or right of my hand, you'll ask, your left or my left? We call to the left of a covariant property because it varies with the point of view. There is only a fact of the matter if you've selected a point of view from which to ask the question. Anyone from your vantage point saying that the pen is to the right of the hand would be wrong. But without a point of reference, there's no fact at all. The truth is just a truth in a frame of reference. This is what we mean by covariant. But if I now asked if the pen is between my hand, you would never ask, well, you're between or my between, because between doesn't change. It's what we call an invariant property. Truth or falsity of an invariant claim does not depend on your frame of reference. It simply is true or false. This lack of dependence on a viewpoint means that we treat invariant propositions specially. We take them to be true of reality itself. If something is the case no matter who sees it, no matter where they see it from, no matter what, then we think there must really be something there to be seen. Einstein's theory of relativity takes distance and turns it from the invariant fact Newton thought it was, that is something true of the world itself, and makes it a mere covariant fact, something that's just true of how I see the world, not of the world itself. The same is the case for time. Durations stretch, that is, time slows down when you move, and the faster you go, the slower your watch goes when observed by someone at rest. Putting these two together, he shows that our common sense picture of adding velocities in the airport is wrong. Recall that I'm on the people mover going 2 miles an hour, while someone else walks past at 5 miles an hour and still another person watches from Starbucks. According to Newton, if I want to calculate how fast the person passes me is really moving, then I add my speed to the speed I see him walking. 2 plus 5 is 7. But Einstein calculates that it will be slightly less. Now, for the speeds of daily life, this decrease isn't noticeable, but the effects makes it so. If something is moving the speed of light, adding it any other velocity to it keeps it moving the speed of light. Thus, the speed of light is not only constant, but a limiting speed. There is no way to get something to move faster. Einstein realized that this led to a startling conclusion. If we think not just about the individual particles, but the interactions between particles, we have to have certain conservation laws observed. This includes the conservation of momentum and the conservation of energy. You can't get energy or momentum from nowhere, and what goes in must come out. Momentum is the mass multiplied by the velocity, and the kinetic energy, or energy of motion of a body, is 1/2 the mass times the velocity squared. But since the theory of relativity makes the velocity something that's dependent on the frame of reference, these quantities have to be adjusted as well, because they have to remain the same going in and coming out. The only way to make that work is for the mass to change in order to compensate for the way the velocity changes. As a result, the faster you go, the heavier you get. As you approach the speed of light, your mass approaches infinity as measured by someone at rest. This means there is a lowest rest, the so-called rest mass, that gets measured in the frame in which the thing is at rest. A shocking result of this is that mass becomes seen as a form of energy. We knew that energy came in different forms, heat, light, motion, But going back to Newton, we thought that mass was something different. It was a state of being, a property unto itself. The theory of relativity contends that it's just another form of energy. This is summed up in the most famous equation in all of science, E equals mc squared. That is, the amount of energy pent up in a massive object is equal to the mass of the object multiplied by the square of the speed of light. This gives us another reason nothing can move faster than the speed of light. As something gets heavier, it needs more of a push to accelerate it. But at the speed of light, its mass becomes infinite. To accelerate an infinitely heavy object, even a teensy bit, would need a push that generates an infinite force. But that would require infinite energy. And you can't have that. So, traveling faster than the speed of light is not an engineering problem we haven't figured out how to solve. It's something that, according to Einstein's theory, cannot be done. Einstein's college professor, Hermann Minkowski, was stunned when he read Einstein's work. Stunned in part because of what it said about the universe, and even more stunned that it was Einstein who figured it out. In his autobiographical notes, Einstein lists Minkowski as one of his great teachers, but you never would have known it from his attendance, and Minkowski referred to Einstein as a lazy dog. Now, in 1908, Minkowski gave a speech to a meeting of the Assembly of Natural Scientists and Physicians at Cologne, entitled Space and Time, where he sets out what we now call the geometric interpretation of the special theory of relativity. When Einstein first read the remarks, he was annoyed. Typical of Minkowski and those mathematicians, he thought, to take a perfectly good theory and reformulate it in a mathematical way that no one can understand. He thought that Minkowski was making the theory pretty, but not really saying anything. And then Einstein thought about it some more and realized that Minkowski was doing something incredibly profound. His old professor taught him what his own theory really said about the universe. The introduction to the talk ends with this notable claim. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality. What Minkowski was telling Einstein is that Einstein is telling us that we live in a four-dimensional universe. Now, let me explain what I mean by the word dimension here. I mean the number of numbers needed to specify a location. Suburban houses, for example, have one number in their address, their house number. Right? Given this number, I know how far down the street to go to get to a house. One dimension. To find a building in Manhattan, I need two numbers, the street and the avenue, two-dimensional space. To find an office in Manhattan, I need the street and the avenue numbers, but I also need a third number, the floor, three-dimensional space. To specify a meeting in that office, I now need a fourth number, the time. That's all that's meant when we say that time is the fourth dimension. In other words, to uniquely specify an event, I need four numbers, 3 to nail down where, and 1 to nail down when. Now, thinkers as far back as Gottfried Leibniz in the 17th century had that much, but they still claimed that there was a fundamental difference between the three spatial dimensions and time. They were different kinds of things. What Minkowski realizes is that the universe that Einstein gives us weaves space and time together into a single fabric, a fabric whose plaid pattern will appear different to different observers moving at different speeds. But which is the reality underlying all of these different observations? We live not in Newton's three-dimensional absolute space flowing through one-dimensional absolute time. Instead, we live in a single four-dimensional space-time. Each of us experiences this reality differently, but through the equations in the theory of relativity, we can calculate the underlying truth about the observable four-dimensional space-time manifold. We buy into the idea that seeing is believing, but what we get from the theory of relativity is that seeing requires a perspective, which gives you merely a part of the story. Reality is not what we see, since we only see it through our own limited vantage point. It's something larger and stranger, and from Einstein forward, we can now only see the world in this larger way. This is a point that we see explored in the arts of the time. The movement of Cubism in painting was an attempt to do to the canvas what Einstein and Minkowski were pointing out in the equations. Now, since the 15th century, one-point perspective was used in painting to make a flat image appear to have depth. The artist, by picking a focal point within or outside of the picture, could draw lines radiating out that would serve as the guides for the appropriate slant to give a sense of 3 dimensions to a work that was trapped on a 2-dimensional surface. But Pablo Picasso thought that this extension to a mere 3rd dimension was itself too limiting. He sought to capture the underlying reality contained in the multiplicity of spatial and temporal perspectives. That is, he wanted his 2-dimensional paintings to capture the 4-dimensional nature of his subjects. He and his fellow cubists took the subject to be painted and broke it down into elements, cubes, which were each painted from a different perspective of space and time, and then reassembled into a single package, giving all of the viewpoints equal access to the truth they convey. One of my favorite Cubist works is Juan Gris's portrait of Pablo Picasso. It seems only fair that if Picasso was going to break things down into basic elements and reassemble them from multiple perspectives of space and time, that someone did it to him. Sort of like the pot painting the kettle black, except that the kettle is now inside out with its handle coming out of its bottom. But like Einstein's space-time continuum, the higher level truths look strange to those of us who are trapped in our own reference frame, thinking that we have complete access to reality itself. Picasso and the others' Cubist works were meant to be unsettling, to shock us out of our complacency of perspective, to realize that to glimpse reality, we would need to become unstuck in time. That phrase, unstuck in time, was used by the writer Kurt Vonnegut in his masterpiece Slaughterhouse-Five to describe the state of his protagonist, Billy Pilgrim, who was abducted by aliens from the planet Trafalmador, who were capable of time travel. Being freed from linear time, they saw the universe quite differently. Reality no longer had a fixed past and an open future. Instead, reality is the full 4-dimensional nature of being, as Minkowski described in Einstein. In one poignant passage, Billy Pilgrim says, "The most important thing I learned from Trafalmador was that when a person dies, he only appears to die. He's still very much alive in the past, so it is very silly for people to cry at his funeral. All moments, past, present, and future, always have existed, always will exist. The Trafalmadorians can look at the different moments just the way that we can look at a stretch of the Rocky Mountains, for instance. They can see how permanent all the moments are, and they can look at any moment that interests them. It's just an illusion we have here on Earth that one moment follows another one, like beads on a string, and that once that moment is gone, it's gone forever. When a Trafalmadorian sees a corpse, all he thinks is that the dead person is in a bad condition in that particular moment, but that the same person is just fine in plenty of other moments. Now, when I myself hear that somebody is dead, I simply shrug and say what the Trafalmadorians say about dead people, which is, so it goes." Isn't that amazing writing? I love Vonnegut. We believe ourselves to be who we are now. We may be influenced by where we've come from and what we've experienced, but we are what we currently are, and we can have hopes and plans for what will be, but that future is a future to come, to be shaped at that time. But our entire picture of ourselves as projects hinges on the old Newtonian notion of time. We now see that we are always who we were and who we will be. We're 4-dimensional selves. Billy Pilgrim seems crazy to us because we are unaware of that dimension, like the shapes were in Abbott's Flatland were discussed in the last conversation. Einstein's world is the stuff of fantasy, envisioned in the art of the previous century. What we find in the works of Vonnegut and Picasso in Einstein's century are attempts to make sense of what the universe looks like from this new perspective that we get from the theory of relativity. That is, the first theory of relativity. 11 years later, Einstein would rework his theory, expand it and extend it to challenge our picture of reality in even more radical ways. To understand that, we'll need an entire discussion focused on the general theory of relativity.